So we have looked at the energy and reactions and saw there's potential and kinetic energy. We have seen our phases change, and we've actually graphed them on a heating curve. Now we're actually going to figure out mathematically how much heat is required to do certain things. So we can calculate the amount of energy or heat absorbed or released in each section of our heating curve by using one of three formulas. We can use specific heat, we can use latent heat of fusion, and we can use latent heat of vaporization. So we're going to take a look at each specific one and see where they are on the graph and how we can actually use these formulas. Okay, so specific heat, also known, I like to call it as Q equals MCAT, okay? Because the delta, which is the triangle, looks like an A. So specific heat, so Q, okay, and we're going to see Q a lot. Q is the energy or heat. It can be negative because it's absorbed and is endothermic, or it can be positive because heat is released and it's exothermic, okay? We look at mass in grams. We look at C, which is specific heat. Everything has its own specific heat. Okay, and this is the amount of energy required to raise 1 gram of that substance 1 degree Celsius. And then delta T, they go together. Delta means change. Change means you're going to subtract. Okay, it's a change in temperature. We're going to take our final temperature and subtract our initial temperature. So let's take a look at a question. So I have 5 grams of copper and I heat it from 20 degrees Celsius to 80 degrees Celsius. I want to know how much energy was used to heat copper. Copper specific heat capacity is 0.385 joules over gram Celsius. Now, in this problem, I gave you that. Sometimes it won't give you that. So I want to show you where you can find that answer before we come back to this. So if you go to your chemistry reference table and you go to the bottom, okay, there are 10 metals that are very common for us to use. And if you notice, the second column, okay, has our specific heat listed. And you can see they're all different, okay? The other thing I want to make mention is if I ask you for this to do water, water has a specific heat, okay, and it is right here. So specific heat of water. Now notice that there are 3 different values, and that's because there's 3 different phases. When water is a solid, it's 2.05. When it's gas, or steam, it's 2.02, and when it's water, it's 4.18. That is very important. We're going to see that later when we do a problem when we use all 3 of them. So make sure when you're doing water, you're understanding what phase you're in to use that specific one. So again, here's our problem, okay? The thing you want to do is you want to write down your variables and then you want to use your problem to fill them in. So again, 5 grams of copper was heated from 20 degrees Celsius to 80 degrees Celsius. How much energy was used to heat the copper? Okay. Since it's asking me how much energy, Q is going to be a question mark. The mass is going to be 5 grams, okay, because that's what it says right here. Okay. Our specific heat is 0.385, and that was given to me. Again, if not, I can look at my reference table. Okay. And then my change in temperature is I start with my final, which is 80, minus my initial, which is 20, to get me 60. So then I just plug it into my formula. This one's nice because Q is already by itself, so I don't have to do a lot of manipulating of the formula. If Q is not by itself, or sorry, if the letter that you're looking for is not by yourself, you may have to do some manipulating, and we're going to see one of those. Okay, so 5 times 0.385 times 60 gives me 115.5 joules. That's how much energy is required to heat up my copper from 20 degrees to 80 degrees. Okay, let's try another one. Okay, I have a temperature of a sample of iron with a that has a mass of 10 grams, and it goes from 50.4 to 25 degrees with the release of heat of 114 joules. What is the specific heat of iron? Again, I'm going to put in my information. Okay. So I have 50.4 to 25, and I did this backwards. It should have been, I should have said change from 25 to 50, so sorry about that. But it's still the same problem, so I want to show you that. So here's my formula. 114 equals 10 times the question mark times 25. So I'm going to take 114, and when I multiply 10 by 25.4, I get 254. To get my question mark by itself, I have to divide both sides by it, and my answer is 0.449 joules over kilograms. Joules over grams degrees Celsius. So that's kind of how that works. All right, latent heat of vaporization. This should be on the next slide. Heat of vaporization. Every substance has its own heat of vaporization. And so before we get into our problem, I kind of want to show you that on your reference table. Okay. So here, okay, if you notice, they don't have it for metals, they don't have it for your organic substances. You can always look it up, but mostly we're going to use water for a lot of it, or we're going to give you it in our problems. But the heat of vaporization of water is 2,260 joules per gram. It takes a lot of energy to go from a liquid to a gas. Okay, it takes a lot of energy. Okay. So if I had 35 grams of water, how much heat would it take for my water to turn into steam? Again, I'm going to write down my different pieces. I'm looking for the amount of energy or heat. The mass was given to me at 375, and my heat of fusion came from my reference table of 2,260. I just plug it into my formula, and I multiply. And again, you can do the same thing. You just, if you're, whatever you have, whatever letter you're trying to find for, you just have to manipulate your formula so it's by itself. Okay, in this case, Q is by itself. Okay, latent heat of fusion. Okay, this is when a liquid, when a solid becomes a liquid. And again, everything has its own heat of fusion. Going back, okay, again, it's not listed for our metals, but for our water, okay, for our water, it is at 334. It doesn't take as much energy to go from a solid to a liquid as it does for it to go from a liquid to a gas. Okay. Okay. Present. Okay. So if I still have that 375 grams, but this time it's ice, I want to know how much energy it's going to take for that ice to become water. So again, I'm going to write down my symbols. Oh, and that should say H of V, or H of F, not H of V. Sorry about that. That was an oversight. I'm looking for my heat. Again, my mass is 375, but here my heat of fusion is 334. Again, I just plug it into my equation, and I get that it's 125,250 joules. Okay, it's a little bit smaller than my heat of vaporization. Actually, it's a lot smaller. Okay, so you can figure out how much heat is in a total curve. Okay, to do that, we have to keep doing these different sections over and over again. And so we're going to follow this problem about how much heat is required for 100 grams block of ice to become steam. And in the next one, I actually update the fact that I gave you temperatures. So my 100-gram block of ice starts at negative 25 degrees Celsius, and becomes steam at 110. Now, here's how it works on our graph. Everything that's slanted, okay, everything that's slanted uses Q equals MCAT, okay? Everything that's plateaued is going to either use heat of fusion or heat of vaporization. So I'm going to do MCAT, okay? My Q is unknown. It's 100 grams. Okay, I'm using 2.05 because I'm using the specific heat of ice. And my change in temperature is 25 degrees because my final temperature is 0, but I want to subtract a negative 25. That becomes positive 25. So I plug it all in, and it's 5,125 joules. My next section is a flat section, and it's when a solid becomes a liquid. So I want to do latent heat of fusion. I don't need to worry about my temperature right now. I just need to know that I'm looking for Q. My mass is still 100 grams. The whole purpose of this, remember, is none of your stuff is lost. None of your matter is lost. You can't lose it. Okay, remember, law of conservation of matter. You can't lose, gain, or destroy. Okay, so everything's staying 100. And then it's 334. So 100 times 334 gives me 33,400 joules. Okay. Now I'm going to go up another incline, so I'm going to use MCAT. This time, my Q is still unknown. My mass is 100. That doesn't change. My C changes to 4.18 because that's the specific heat of water as a liquid. And my change in temperature goes from 0 to 100 because 0 is the temperature, the melting point temperature, and 100 is my boiling point. So it's 100. So I'm going to multiply those together, and I get 41,800. Okay. I get to another plateau going from a liquid to a gas, which is my latent heat of vaporization. So I'm going to write out that formula. So my Q is still unknown. My M is still 100, but my heat of vaporization is 2,260. Again, getting from the reference table. Put it in my formula, 226,000 joules. And these numbers are getting very big, and we're going to see what happens when they get very big. Okay. So my last step is to figure out how much energy to get that steam from 100 to 110. Again, my Q is unknown. My mass stays 100. My specific heat is 2.02. Again, coming from that reference table, I'm looking at the one for steam. And then my change in temperature is 10 degrees because it's 10 degrees from 100 to 110. So I plug all that in. I get 2,020 joules. Now, I'm going to take all of that information, all of those calculations, and I'm going to add them together. So 5,125, 33,400, 41,800, 226,000, 2,020 gives me 308,345 joules. So to raise the temperature of a block of ice from negative 25 degrees Celsius to a thing of steam at 110, it requires that much energy. And that is the math of heat.